In the last class, we discussed about some basic properties of graph theory. We talked about the topic of, we talked about the topics like incidence and degrees of the vertices, and some fundamental rules have been considered over there. Now, in this particular section, I'm going to discuss one of the most important and unsolved mystery of graph theory, which is called isomorphism between the two graphs. You already know from group theory that what is the definition of isomorphism. Isomorphic, when I say that two structures are isomorphic, that means characteristically the two structures are similar. So if structurally the two graphs are similar, we will consider the two graphs to be isomorphic. Okay, so first of all, let us try to understand what do we actually mean by that. Okay, and then I'm going to show you something which I think you are going to find very interesting. So whatever is written over here regarding the isomorphism between the two graphs, I'm coming to that sentences later on. But first of all, let us try to understand the definition of isomorphism by citing one example. And the example that I'm considering is the following. Just try to understand it very carefully. Suppose I'm considering a graph like this. The graph containing okay, and let us not name these vertices as V1, V2. Let us, for simplicity, let us call these vertices as 1, 2, 3, and 4. And I'm going to connect these by the edges in the following manner. So how many edges are there? 4 edges are present in this particular graph. Let us name this graph as capital G. And remember, this type of graphs that I'm discussing right now, these are actually called undirected graphs, because the direction of the graph is not mentioned. Okay, whether you move in clockwise direction or in anti-clockwise direction, that doesn't matter. But if I put the arrowheads, if I show the movement of making the edges from one vertex to the other, then this particular this direction, this movement is very important. And those graphs are actually called the directed graphs. All the properties of undirected graphs can be carried forward to the study of directed graphs. So right now, I'm not going to consider the directed graphs. I'm going to stick to the undirected graphs only. Now, what I'm going to do is that I'm going to distort this structure a little bit. So how am I going to distort? Let us try to find out. I'm again considering the same 4 vertices, 1, 2, and 3, 4, like this. And I'm going to join them in the following manner. So 1 and 2 are being joined like this. This is the edge. And then I'm going to join 2 and 4 like this. And then I'm going to join 4 and 3 like this. And then I'm going to join 1 and 3 like this. This is one thing that I'm doing. And let us name this graph as G prime. Again, I'm considering a graph like 1, 2. And I'm writing 3. Okay, this I'm considering as 3, and this I'm considering as 4. Okay, and I'm going to join them in the following manner. So 1 is being joined like this, 1 to 2, 1 and 2 are connected, 2 and 3 are connected, 3 and 4 are connected like this, and lastly, I'm going to join them in the following manner. So this is G double prime. Now, thing is that why we need to do this kind of things, this kind of activities. If we are going to draw a kind of circuit, if we are going to embed a kind of circuit where the structure of the circuit gives you the algorithm of something, some computer architecture, you are going to put this the algorithm of this architecture, you are going to embed this algorithm with the help of circuits, then you can join these two vertices in this number of vertices in any way. That means if there are two vertices, 1 and 2, it doesn't matter whether you are joining them by a straight wire, or you are joining these two vertices like this, or you are joining these two vertices like that. It doesn't matter. So it depends upon what system is available and what type of availability is present. What are the options as per as per the options given, we are to design our circuits. So it doesn't it is not always the case that we are going to connect the vertices in a circular fashion like this. You can join them in the following manner also. And here the edges are gives you the connectivity between the vertices. Now the question is, suppose in my chip, on my chip, I want this type of embedding. 1, 2, 3, 4. This type of embedding is required. Now somebody is embedding the thing in the following manner: 1, 2, 4, 3. And somebody is embedding in the following manner: 1, 2, 3, 4. So question is that whether these graphs that I have drawn, G prime and G double prime, are they structurally isomorphic to G? If capital G and capital G prime are structurally isomorphic, that means it doesn't it doesn't matter whether I connect in the way as is shown in G prime, or whether we are going to connect in the way as shown in G double prime. But if these graphs G and G prime or G and G double prime, if they are not isomorphic, then we cannot consider this type of connectivity. If I want capital G, we cannot consider this type of connectivity as shown in G prime. And if G and G double prime are not isomorphic, we cannot consider this type of connectivities that has been shown in G prime to get capital G. So first of all, you have to study the structure of these graphs. Now carefully observe. If we observe this figure, G double prime, first of all, what do we actually find? Carefully observe and try to get your visualization in a three-dimensional direction. So you see that some sort of distortion that I'm going to make on the structure given. What sort of distortion? Suppose you are, I hope that you are able to see my cursor. I am actually considering the vertex 3. I am unhooking the vertex. I'm unhooking the vertex, and I am moving this vertex perpendicular to my direction, my observation, and I'm going to make this turn this particular thing. I'm going to turn this particular thing in such a manner by giving this in a three-dimensional rotation to obtain 3 in place of 4 and getting 4 in place of 3. And this connectivity 1, 2, 3, 4, that connectivity will be retained. If I consider the figure G, you will see that 1 and 2 are connected. So 1, 2 and 1, 2 are connected. If I give it this kind of rotation or this kind of distortion, 2 and 3 are connected. So 2 and 3 are connected. 3, 4 are connected. 3, 4 are connected. And 4, 1 is connected. So 4, 1 are also connected. So you see that G double prime and G, they are actually isomorphic. And if G and G double prime are isomorphic, then we write this as G is isomorphic to G double prime. What about G prime? Now, if I consider the same thing, if I unhook 3 and give it a three-dimensional rotation perpendicular to my observation and take it to 3, then you will not get, you are not going to get the same graph, isn't it? So you are not going to get the same graph, because as you see that 1 and 3 are connected, 1 and 3 are connected, but here 1 and 3 are not connected. Okay, 2 and 4 are connected, so here 2 and 4 are not connected. So first of all, at a first instance, it seems as if they are not isomorphic. But if careful observation shows us that once I give this type of rotation, if I consider, if I give a move turn and bring it 3 in this position and 4 in this position, now apparently it seems that graph G and graph G prime, they are not same. But what will happen if I rename the vertices? If I rename the vertices, if I rename 4, if I replace the name of the vertex 4 by 3, and if I replace the name of the vertex 3 by 4, you are going to get the same graph as has been described in capital G. So actually, this graph G prime is also a graph which is isomorphic to G. So this I'm going to consider also to draw the graph capital G. So both these graphs, G, G prime, G double prime, and G, G, sorry, it should be G prime. These two pairs, G, G, G double prime and G, G prime, they are both isomorphic to one another. Okay, so now let us try to find out what is written over here. Two graphs G and G prime are said to be isomorphic to each other if there is a one-to-one correspondence between their vertices and between their edges, such that the incidence relationship is preserved. Okay, so we have to consider at the end of the day whether the incidence relationship, whatever distortion we give to the graphs or whatever movements we make, the incidence relationship must be preserved over there. After giving a distortion, the incidence relationship must be automatically reserved, or we have to rename the vertices to preserve the incidence relationship. That we have to decide. So there are some fundamental rules by which we can, here are some examples. As you can see, some examples of isomorphic graphs are shown. Okay, you can later visit these examples to find out whether these are isomorphic or not. They are already mentioned to be isomorphic. Some fundamental rules that you have to consider to study the isomorphism between the two graphs. These rules are: the same number of vertices. The two graphs must have the same number of vertices. The two graphs must have the same number of edges, and equal number of vertices with a given degree. So suppose you are actually in a particular graph, you are getting two vertices having degree 3. So in the isomorphic graph, you are also supposed to get two vertices having degree 3. So equal number of vertices with a given degree. That is also a kind of a thing that need to be checked to find the isomorphism between the two graphs. Let us consider these two graphs which are actually not isomorphic. Now, if I try to apply the rule that has been mentioned just now, you will find that if this is my graph G and this is my graph G prime, you will find that number of vertices in G is actually 6, and number of vertices in G prime is also 6. So this vertices relationship is actually preserved. Number of edges in capital G, how many edges are there? 1, 2, 3, 4, 5. 5 edges are there. It is 5. And number of edges in G prime, 1, 2, 3, 4, 5. 5 edges. This is also preserved. No problem. Now you can see that in this particular graph, one pendant vertex is there. Three vertex are there with degree 1. Okay, so this is one, this is the vertex U, V, and this one, they are having the degree 1. Here also we have got 3 vertices having degree 1. No problem. We are getting a vertex over here which is having degree 3. Here also you are getting a vertex which is degree 3, which is having degree 3. So that is also preserved. And this vertex and that vertex have degree 2. Here also we are going to get these two vertices which are having degree 2. So all the properties, all the 3 properties that have been mentioned in the previous page all the properties have been preserved over here, but yet capital G is not isomorphic to G prime. And therefore, we have to study why is it so. Now you see that one fundamental thing, you cannot given any distortion to the graph capital G to get graph G prime or vice versa. Why? Because you see in this particular graph capital G, this vertex which is having degree 3 is connected to two pendant vertices. Two pendant vertices are connected to this vertex with degree 3. But here, this, if the two graphs need to be isomorphic, then the vertex X and the vertex Y need to correspond with one another. And if it is so, we find that this vertex X having degree 3 is connected to two pendant vertices, but here this vertex Y, which corresponds to X, is connected to only one pendant vertex. And this is the structural dissimilarity between the two graphs, and therefore the two graphs are not isomorphic. So you can say that since the three rules have been defined in the previous page, and all the three rules are getting satisfied, but yet the graphs are coming as non-symmetric graphs, non-isomorphic graphs. So what is the general rule to find that two isomorphic graphs? So you see that in this particular paragraph, it is written that finding a simple and efficient criteria for detection of isomorphism is still actively pursued and is an important unsolved problem in graph theory. No general rule has yet been developed, no universal theory has not yet been developed, which can find two graphs to be isomorphic. But in chapter 11, you are going to see that several algorithms have been proposed. Their computer programs have been shown to you, where to some extent you can find the graphs to be isomorphic, but yet those algorithms in that chapter cannot find isomorphism between all types of graphs. Okay. Now I am going to show you something which you may find very interesting. So the thing that I'm going to show you is this one. As you can see that I am actually presenting to you a portal which is actually known as Maple. It is a mathematical software which can do various engineering, mathematical and statistical calculation. So with the help of this Maple, I do not know what sort of algorithm that I'm going to show you right now. First of all, let me give you the practical example about some problems on graph theory with the help of this Maple software, and then I'm going to make my comment on this. So in this Maple portal, if you want to do the graph theoretic calculations, then you have to first of all make this type of arguments over there. So with graph theory, this is the command that you need to make over here, and once you do it, your graph theoretic calculation portal will be activated. Okay, now it is activated and you are in a position to do the graph theory right now. Now I'm going to consider the two graphs that I have discussed just now. Okay, and I'm going to study the isomorphism between the two graphs. So what are the commands? How we can find that two graphs are isomorphic? Is it possible to use this particular software to study the isomorphism between the two graphs? Yeah, first of all, you have to define the graph. So we are naming the graph as G1. Now, probably if you have drawn my figure was a square. I considered 4 vertices. Counterclockwise, I considered their vertex names 1, 2, 3, 4, like this. If you have forgotten, now I'm going to make this graph over here. So graph, this command I'm making, and this is the way by which that will be done. 1, 1 and 2. When I'm writing 1 comma 2, that means 1 and 2 are connected. Then 2 is connected to 3. Then 3 is connected to 4, and 4 is connected to 1. My command is done. I'm finishing the bracket, and this graph is being read. So it is saying that an undirected, unweighted graph is given with 4 vertices and 4 edges. Now I'm going to do the second one. In the second one, I'm more interested about the graph G prime. Okay, so I'm going to do the trail in the following manner. 1 and 2 are connected, and 2 is connected to 4, and 4 is connected to 3, and 3 is connected to 1. And then I'm going to put enter. So it is saying that this graph 2 is an undirected graph with 4 vertices and 4 edges. If you want to see how these two graphs look like, then you can put this command draw graph. You can put this command draw graph, and you can write these two graphs G1 and G2 over there, and you can give the structure a circular structure. Okay, and hopefully my command is correct. No, I have done some mistakes. Not I should, oh yeah, I should write not circular, I should write circle. Circle, yeah. Now if I draw this graph, you can see yeah. So you see these graphs are actually being shown to you. I considered these graphs, just I drew these particular graphs, and I have given it a circular structure, isn't it? So kind of 1 is connected to 2, and 2 is connected to 3, and 3 is connected to 4, and 1 is connected to 2, and 2 is connected to 4, and 4 is connected to 3, and 3 is connected to 1. I want to check whether the two graphs are isomorphic or not. So I will write this command is isomorphic. Is isomorphic, capital G1 and G2. So it is studying is the two graph, is the pair isomorphic. Okay, so let us trying to test it. The answer is true. Yeah, this pair is isomorphic to one another. Now in some way they have written some sort of algorithm. What algorithm is written is they are playing is playing behind the screen. You can get the algorithm from this help section. In help section you are going to get the algorithm, and I'm going to show you. Suppose you want to know what sort of mathematics they are playing over here. So you can go to the help section, and you can type in graph isomorphism, graph theory isomorphic. Okay, because it is not possible for us always to remember the commands. So here they have given you a short description of the program that is being run. Okay, so the calling sequence they are maintaining is isomorphic G1 and G2, and is isomorphic G1, G2, and phi. Phi is the connection between, phi is the name to assign mapping of graph 1 to graph 2. So phi is a kind of function which is mapping the graph 1 with the graph 2. They are describing the isomorphism property, and then they are giving you actually the commands which are actually needed to, and they have shown you several examples over here. So graph theoretic study can also be done with the help of matrix theory. So some matrix commands are also mentioned over here. Now, specifically, they have not actually mentioned what sort of algorithm they are actually using over here. Okay, so I cannot get any hint of type of algorithm, what sort of algorithm they have applied in this example of finding isomorphism between the two graphs is actually not known to me, and they are not telling me this. Now I have to look for some other parts of the graph theory. If it is mentioned, then we can take a note of that. Okay. So we using software, you can find the isomorphism between the two graphs, but you have to keep in mind that to some extent this can be done, not always. Not always. No universal rule has yet been developed, and to study the isomorphic property of between the two graphs. So let's get back to the note that I was actually uh, sharing with you. And this particular note that I have shared, this note is actually already posted in the Google Classroom. So probably if you are thinking that you do not have the book, it is wrong. I posted it a long time ago, 5 weeks ago. I posted it when I was teaching you the mathematical logic. Now, then an important property that comes into play is called the subgraph. Just like set has all subset, and group has a subgroup, and ring has a subring, vector space has a subspace. Every graph is associated with a subgraph. And one trivial subgraph, if you draw a graph, one trivial subgraph is the graph itself. Just like we said that with respect to a set A, the set itself the subset, then the graph itself the subgraph of it. And not only this, the null graph is also a kind of subgraph. Say for example, if I draw, again I'm going to draw this figure, v1 and v2, and the edge is E. This is my graph G. Now if I delete this edge E, I'll be left with two vertices only, v1 and v2, which is the null graph. This will be the subset of the graph capital G. Not only this, the graph capital G will also be the subset of itself. This type of subgraphs are called actually the trivial subgraphs. But apart from that, other subgraphs are also possible. So with an example, I'm going to show, the example is already shown over here. Non-trivial subgraph of the given graph. So for example, if I consider this graph, and from this graph, if I omit this particular edge, if I omit this particular edge, and this particular edge, and also these vertices are deleted, okay, and I'm retaining only this vertex, this vertex, this vertex, and this vertex, and their individual connections. Okay, so if I retain this, you are going to be left with this particular figure, this particular structure, which is B. Then you see that the connectivity of the vertices with respect to some edges, that has not been distorted. The same connectivity has been retained. Only thing is that some of the edges and some of the vertices are missing from the picture. Some of the vertices and some of the edges are missing from the picture. So if this is the case, then we can consider the structure drawn in this part B is the subgraph of the graph which has been drawn in part A. So what are the definitions of subgraphs? Let us try to find it out. So the following observations are very important with respect to the study of subgraphs of a given graph. Every graph is its own subgraph. A subgraph of a subgraph of G is a subgraph of G. A single vertex in a graph capital G is a subgraph of G, and single edge in G together with its n vertices is also a subgraph of G. And how do we identify the subgraphs? That is important. So it is written that a graph G is said to be a subgraph of a graph capital G if all the vertices and all the edges of G are in G, and each edge of small g has the same end vertices in G as in capital G. So in a simple word, the connectivity of the vertices should be retained in the same way as has been retained in the mother graph. If you can do so, you are going to get the subgraphs. Now, different types of subgraphs are present. Edge disjoint subgraphs are kind of subgraphs which you can consider. So you just read this particular paragraph and try to relate this paragraph with the above figure. You are going to understand. Some mathematical examples and puzzles are there that you can skip for the time being. You can the problems are of the mathematical problems, the puzzles and the games related problems are actually not going to come in the examination. And if you are interested in graph theory, you can always visit, because the note is with you and you can study it. Nobody is actually telling you to not to study, but to just save time, you can skip them from the time for the time being, to revisit them again when you find time. So skipping them, I'm going to come to this particular section, which is called walks, paths, and circuits. Now, let us consider this figure, which is given over here. Okay, so three concepts are actually very important, play an important role in the study of graph theory. One is called walk, one is called path, and one is called circuit. Actually, what are the connections between these three items? If we consider walk, then this path and this circuit are the two parts, two types of walks. Okay, so they are connected in this particular fashion. So walk is the mother, and these are the two siblings. Okay, path and circuit. So we are going to learn about them here. First of all, let us start with the definition of walk. A walk is defined as a finite alternating sequence of vertices and edges, beginning and ending with vertices, such that each edge is incident with the vertices preceding and following it. No edge appears more than once in a walk. So you see the most important part in this particular diagram, in this particular definition, is the part that the edge shouldn't repeat itself. If I consider this particular figure, with respect to this particular figure, if I start from this vertex, and if I move along this edge A and come to vertex V2, and then if I move along this edge B and come to vertex V3, and then if I trace this line C and come to vertex V3 once again, and then we come to the vertex V4 and then V2, then this will not be a walk. Why? Because if I move along this line, and if I trace this particular vertex, this part, no, here edge appears more than once in a walk. No edge is appearing more than, no, this can be done because I am not retracing the edge. So this can be done. See, if I move along this edge, if I go like this, and if I consider this and then this and this, all the edges A, B, C, D, E, they have been traced only once. Okay, I have come down from V1 to V2 by tracing A only once. I have come to V3 by tracing B only once. Then again I have give a circular motion and come back to V3 by tracing the edge C once, and then D once. I come by tracing D once, I come to V4, and then I move back to V2. So move back to V2. But the point is that I cannot trace. This will not be walk. It's because this can be worked because the edges are not being repeated. The edges are not being repeated. Now, if I from V2, if I try to go back to V1, then this edge, this particular edge A will repeat itself twice. Okay, up to this was all right. V1, V2, V3, V1A, V2B, V3C, V3, D, V4, and E, V2. Up to this was all right. But if I want to come back to V5 by tracing F, that is all right. But I cannot move back. I cannot go back to V1 because in this particular case, A will repeat itself twice. And therefore, this type of sequence will be a walk. Okay. Now, what is path? An open walk is actually called a path, and a closed walk is actually called a circuit. That is the most important thing. Now, if I consider this particular figure, I think it would be nice if I draw it. If I move along this line, and then if I go along this line, and then if I retrace it, and then if I come to V4, and then if I go to V2 and then to V5, if I consider this particular thing, so starting from V1, I'm coming to V5 by retracing this particular edges, then I will actually, I'm going to get a path over here. But because it is a kind of open walk. Okay. But if your walk is not open, then you are acha. One another thing is that in path, your edge shouldn't repeat it. Your vertex should not repeat itself. So yeah, this will be a walk definitely, but it will not be a path because here the vertex V3 is being repeated twice. So actually the open walk is this one. So you are coming to V1 to V2 and then to V3 and then to V4. But if you cannot retrace V3 twice. So if you retrace V3 twice, then it will be a walk, but it will not be a path. So in path, your vertex shouldn't repeat itself more than once. That is a very important point, and that has been mentioned over here. So an open walk in which no vertex appears more than once is called a path. And the number of edges that are actually present in a path, these are called the length of the path. Okay. So if I consider the simple example as before, this example is an open walk as well as it is a path. What is the length of this path? This length of this path is 1 because only one edge is present in this particular diagram. Okay. Since the time is almost complete, so I'm going to stop over here right now. We're going to continue with this particular examples in the next class. Okay, we're going to discuss in more details about some other parts, some other sections. And we're going to continue about paths and circuits in the next class. We are going to stop at this point. Hope you have understood. So see you in the next class. Till then, bye.